welcome to this problem solving video. We are going to be solving problem 3-153 in the Shigley textbook. And so I've written out the problem statement here. I'll read it aloud. We have an aluminum alloy cylindrical roller with a diameter of 31.75 millimeters and length 50.800 millimeters, which rolls on the inside of a cast iron ring having an inside radius of 152.4 millimeters, which is 50.8 millimeters thick. Find the maximum contact force F that can be used if the shear stress is not to exceed 27.5 megapascals. So this question is asking you to use Hertzian contact for a cylinder on a cylinder, or in this case, a cylinder inside of a hollow cylinder. So first let's just draw what this question has described for us so we get a better idea of what exactly is going on here. We have this cylindrical roller with a diameter. I'm going to call this D1, where D1 is equal to 31.75 millimeters. And it has a length. Let's draw that dimension. This length is 50.800 millimeters. And this rolls inside of a cast iron ring. So let's move this over. I'll draw the cast iron in pink. There we go. And the cast iron ring has the same length as the roller, or same thickness. And let's see, what else do we have for this? We have the diameter of this ring, D2. It's 52.4 millimeters. Oh wait, that's the radius. That's tricky. Okay, so let's, the diameter is going to be 2 times that. And we got our thickness. Okay, so the other information that we need in order to use the equations that we went through last time for Hertzian contact. So remember, we're going to be using this cylinder-on-cylinder model, which we have equations for the contact area, for the contact pressure, and for all the stresses. So this is how we're going to solve this problem. But what we're going to need that we haven't been given are these elastic constants. So we need the Young's modulus and Poisson's ratio of the aluminum alloy cylindrical roller and the cast iron ring. So you can find this information in the back of your textbook in table A-5 for the aluminum alloy, which is material 1. This is our blue roller. The Young's modulus of aluminum is given in that table as 71.7 gigapascals, and the Poisson's ratio is given as 0.333. Then we also need these constants for the cast iron ring, which is material number 2. Young's modulus of cast iron is 100 gigapascals, and the Poisson's ratio is 0.211. Okay, so now that's all of our givens, and the question asks us to find the maximum contact force F that can be used if the shear stress is not to exceed 27.5 megapascals. So we need to find the maximum shear stress. We want to make sure that that value stays below 27.5 megapascals. Well, if we go back to the information we got last time about this cylinder-on-cylinder model, we know that we achieve this peak in the maximum shear stress at 0.786 times B for the contact, the distance from the contact surface. So that's the first thing that we can go ahead and identify. We're going to be analyzing an element of material at 0.786 times B. That's where our maximum shear stress occurs, and our maximum shear stress there is equal to sigma y minus sigma z over 2. Because remember, at this point, we've crossed this threshold line where sigma x was bigger than sigma y, or smaller than, I guess I should say, in magnitude, and now we're at the point where the magnitude of sigma y is smaller. So the difference between sigma y and sigma z divided by 2 gives us our maximum shear stress in this area of the graph. Okay, so we're going to need equations for sigma y and sigma z. We got those last time. We're also going to need the contact width B. So remember that the location where we have contact here looks something like this, and this width is 2 times B. So we're looking for B. When we take these equations up here, which I'm just going to copy and paste, actually down below, because we're going to need them. So we need sigma z and sigma y. We do not need sigma x. Okay, and in these equations we also see that the maximum pressure, maximum contact pressure shows up, so we're going to need that too. All right, so we have enough equations to solve this problem. It's just going to now be a question of working through it all. So let's copy our equations for maximum contact pressure. And the half width of contact area Okay, now that we've done that, we can start plugging things in. We've got what we need. So let's start with B. We know most of the things that we need to put into that equation. So B is equal to the square root of 2 times F. Now F is ultimately what we're trying to solve for, right? We want to know the maximum force we can apply without exceeding the shear stress that we were told. Okay, and then on the denominator here we have pi times L, which L we were given as 50.8 millimeters, or 0.0508 meters. And now we need the material constants for each of the materials. So Young's Poisson's ratio of the aluminum divided by that Young's modulus, which was 71.7 gigapascals. So giga is 10 to the 9, plus 1 minus Poisson's ratio of cast iron, which is 0.211, that's squared, divided by 100 gigapascals. All right, and all of that divided by 1 over the first diameter, which is 0.03175, minus 1 over the second diameter, which we need to do, remember it's 2 times 152.4 millimeters, so that ends up giving you 0.3048 meters. Okay, so if you plug all this into your calculator, you should find that this is equal to square root of 2 times F over, so we got 0.1596 on the denominator here. I got 2.1955 times 10 to the negative 11 in this numerator. And then down here we get 28.215. Right, simplify a little bit further and we end up with 3.123 times 10 to the negative 6 times square root of F. There's an expression for our contact half width of area in terms of F, which is what we want to solve for. Okay, so now let's keep on going. We need to find the maximum contact pressure. And that equation was 2 times F divided by pi times B times the length. So 2 times F divided by pi times B, which again is, we're just going to plug in what we just found for B. So I'm just going to copy and paste that the lazy way. And we also need down here to multiply by the length, which was 0.0508 meters. And when we do that, we find that this turns into 4.013 times 10 to the 6th power times the square root of F. Because remember, this square root of F is going to cancel out with, this is the square root of F squared. That's the same thing as F. Maybe that's more confusing to write it there. In any case, this is what it simplifies to. And now we need to start solving for our stresses. So the first thing I'm going to do, actually just to make our lives a little bit easier, we have in several places this ratio of z squared over b squared, and I think we're going to be able to cancel out variables for that and get it just a number. So let's see, if we do z squared over b squared, that gives us 0.786b. Remember, that's our z location that we want to look at for maximum shear stress, divided by b squared. So the b squareds are going to cancel, and this ratio ends up being 0.6178. Okay, so that just saves us a little bit of time by doing that. And now let's start plugging in for our sigma y. So I'm going to copy this equation put it down here. And let's start plugging. Okay, so negative B max is 4.013 times 10 to the 6 square root f. And all of that multiplied by 1 plus 2 times z squared over b squared, which we found is 0.6178, divided by the square root of 1 plus that same ratio of 0.6178, and minus 2 times z over b, well, that's just going to end up being 0.786. Okay, so again, I can simplify this to get sigma y just in terms of f, and it ends up being negative 745,041 times the square root of f. Let's do sigma z. There we go, let's copy this. Okay, so sigma z equal to negative 4.013 times 10 to the 6 times the square root of f divided by square root of 1 plus 0.6178, which equals negative 3.155 times 10 to the 6 times the square root of f. Okay, so this is all making sense so far. Both of these stresses are giving us negative numbers, and it's compressive stress that develops when we have contact. So this is making sense. The magnitude of sigma z is greater than the magnitude of sigma y, which again is what we would expect. That is what we see in this graph. So everything is checking out so far. Now the next step is to set up our inequality for tau max. So we want tau max to be less than or equal to 27.5 megapascal. That was given in the problem statement. And remember that tau max is equal to sigma y minus sigma z over 2. So if I set this equal to 27.5 times 10 to the 6 and plug in what I have found for sigma y and sigma z, so this is negative 745,041 minus negative 3.155 times 10 to the 6, and this is all times the square root of f divided by 2. If I solve that equation for f, I find that f is equal to 525.95 newtons. And so that is the maximum contact force that could be applied between the roller and the ring without exceeding 27.5 megapascals for the maximum shear stress in this problem. So this is very close to a kind of scenario you might have with a rolling element in a bearing. But keep in mind that all of this is still conceptualizing this as static loads, so we are analyzing this ring and this roller as if nothing is moving. When we get to the point where things are moving, we're going to have to develop some different models to deal with that. But that's all for this video, so I hope you found it helpful, and I hope to see you in the next one.